Jonathan is a software engineer in ThinkCell, so our sponsor, where he's responsible for maintaining core libraries. He's also a member of C++ Standardization Committee, where he serves as the assistant chair of STD ranges and is a frequent conference speaker. As a fun fact, Jonathan just told me that he was preparing numerous papers to Standard Committee and majority of them were rejected. So hopefully his next will be accepted. Yeah. So without further ado, ladies and gentlemen, I give you Jonathan Muller, Functional Programming in C++.
Yeah. So before we get started, I work at ThinkCell, and because someone recently thought that ThinkCell was like an AV company because our logos is on all the conference videos, we are not actually that. We sell a plugin for Microsoft PowerPoint. So if you use PowerPoint for a living, like a bunch of the management consultants do, they all use our plugin because it makes it so much easier to create slides. We have stuff like automatic layout. We've got more chart types. You can directly visualize data from Excel and have it update. We have a slide search, a slide indexer. It's like a bunch of really cool stuff if you were to use PowerPoint. It's entirely written in C++, and because the official APIs aren't good enough, we have a team of reverse engineers, and we sort of hack into PowerPoint to create our own APIs. So on startup, we like patch the process. It's a bunch of cool stuff, really like difficult layout algorithms involved in there, and we are hiring. So if you're really passionate about C++, we definitely are. It's a great place to work. So let's get started. What is functional programming? Functional programming is fundamentally very different from imperative programming. So in imperative program, you specify instructions that manipulate some state in order to achieve a goal. And this is how C and C++ work. You have statements, statements modify memory, and in the end, the memory will contain the bits that you need to represent your solution. This is also how the CPU works, right? You've got assembly instructions, they also modify memory, modify the values in registers, and you directly specify the instructions. Or an IKEA manual is also imperative. It's a sequence of steps you need to follow to assemble your furniture. In contrast, we have declarative programming. In declarative program, you only specify the outcome that you want. And then there is some system that will figure out how to achieve this outcome. You don't specify the individual steps needed to get to that outcome, you just specify the outcome, and then there is some smart system that does it for you. Right? So Haskell, as a functional programming language is declarative. Prolog as a logical programming language is declarative. But also, for example, a formal grammar. Right? A formal grammar isn't a parser. It simply describes what matching strings are. And then there is some parser generator that takes a formal grammar and actually parses your code. And again, for a real-life example, a thermostat in your room. Right? You specify the temperature you want. You don't specify, give me hot air at this temperature for 2 hours. You just say the temperature you want, and then the thermostat will figure out what to heat, what to cool in order to achieve that temperature. And now functional programming is a form of declarative programming by primarily composing functions. So functional programming, unsurprisingly, is about functions. So this is a piece of Haskell, and don't worry, this is the only slide containing Haskell code. So this is the definition of the faculty function in Haskell. It's a function called fac that takes an integer and returns an integer, and then we specify the outcome. We say that the faculty of 0 is 1, and the faculty of n is equal to n times faculty of n minus 1. Right? And these aren't instructions. They're not executed in that order. In fact, you can write those 3 lines in any order. Right? They simply specify the outcome. They specify the definition of the result. Here is a sort function in Haskell. So it takes a list of integers and it returns a list of integers. And we say that the empty list is already sorted. And if you have a list beginning with the value x and some other values, what we do is we sort all the left values, then we insert x, and then we sort all the right values. Where the left values is everything less than x, and the right values is everything greater or equal to x. And here, filter is a function in the standard library, and then when we sort of pass in the less than x and the less than greater or equal to x as a predicate to filter, and this sort of is the way we compose functions in order to achieve a goal. And again, this is purely declarative. It simply specifies the rules for sorting things. Now, why do you care about functional programming? Well, functional programming completely eliminates state. And this is really great. Because if you don't have state, you don't have bugs due to invalid states or broken invariants, right? Simply because you don't have state, so state cannot be invalid, and your invariant's always out. You don't have like a weird shared pointer object graph with like base classes and derived classes, and then something is wrong in there because you don't have any state. You don't have race conditions because race conditions would be like mutable state that is concurrently modified. You don't have state, so you don't have race conditions. And it's also easier to parallelize because you just describe the rules, and then the system can automatically parallelize it if the system is smart enough. So functional programming is so great. Why isn't C++ a functional programming language, right? Well, fundamentally, functional programming does not map neatly to hardware, right? The CPU is very imperative, and so for maximum performance, you want something that maps neatly to hardware, right? So functional programming is harder to optimize because you have to translate your functional programming into the actual instructions on the CPU, right? And the computer might not be able to do it as good as you can do it by hand. It's harder to use native tools like debuggers or profilers because they sort of work by looking at the assembly code, and you can't directly map the assembly back to the functional programming high-level code in a very easy way. It's harder to interact with native libraries and their OS APIs because those aren't written in functional programming languages, so you have some sort of abstraction layer there in between. So using a functional programming language is a trade-off. However, C++ isn't a pure functional programming language, right? You're unforced to use functional programming language, right? We're unforced to use it, we're unforced to use it for everything. And the primary part of functional programming is all about composition. And translated to C++, this means that we can write the building blocks using regular, efficient, optimized, and well-tested C++ code. And then we can compose those building blocks using functional paradigms. And that way, we sort of get the best of both worlds. We've got the performance of C++ and sort of the higher-level simplicity of using functional paradigms. So in this talk, I'm going to look at composition in 3 areas. Composing algorithms, composing functions, and finally, composing I/O. So let's begin with composing algorithms. So I've brought a couple of like lead code style problems. The first one is a very simple one. We are giving a non-empty list of integers, and we want to output the biggest magnitude, so absolute value, of an odd integer in the list. Right? So if these are our numbers, the biggest magnitude of an odd integer is 7, because 7 is the oddest one with the biggest magnitude, -7 there. And this is imperative code to do it, right? Very straightforward. We have a loop. We compute the magnitude of everything. We check whether it's odd. If so, we update the candidate. And in the end, we return the candidate because that's now the maximum, right? It's very straightforward code. And it's very imperative. We directly specify the individual instructions, the individual statements, the individual steps we need to do in order to compute the result. So how do we write that in a more functional programming style? Well, functional programming is all about composition. So I always need to ask yourself, what is the composition here? How can we compose this problem into subproblems? And there are 3 subproblems. One is computing the magnitude of each number. The second one is filtering out even numbers, keeping only the odd ones. And then the third step is finding the maximum of this filtered magnitude list. And we can directly translate that using STL algorithms, for example. So first we call transform on a range, and the predicate just gets the absolute value, and then we store that in a container. And then we copy from that container only the ones that are odd, and then we find the maximum of that container. And here I'm using for STDR, those are the new stored ranges algorithms in C++20, right? So the old algorithms, they take begin and end, and then the new ones in namespace stored ranges, they just take the entire thing. So you save that, like begin end pair, and they also have other nice features. Now, while this is composition, this is eager composition, right? We have to create all these intermediate containers. It's not very functional yet, we have lots of state in there, right? We also eagerly compute all the intermediate results, even if we don't need them. In this example, this isn't a big problem because we do need all the values, but in some other examples, we can save on some computation. And like, it's not very functional because we still have this intermediate state that we need to deal with. So a better way is to use lazy composition. And for that, we can use this views defined in namespace views. So a view is a lazy range where the values are computed on demand. And when you compose those views, this does nothing yet. They merely describe sort of an algorithm that you want to do on the data. And only when you actually start iterating a view or a composed view, you will actually trigger the computation. So as you iterate over a view, each element is lazily computed on demand. Right? And this allows us to write a very functional pipeline style without any manual state. So using views, our example looks like this. So first we compute the magnitude of each number. And for that, we use the transform view. So given our range, we pipe that into the transform view and give it the transformation that we want to do, in this case, the absolute value function. Then we want to filter out the even numbers. So we pipe magnitudes into the filter view. So filters like copy if. And we filter out we keep only the odd ones. And then those first two steps, they haven't done anything. They just created some views. Only when we then pass this view to the std_max algorithm do we actually trigger the computation, right? Max has a loop. It will loop over all the elements of the input range. In those case, here the input range is a view. And so as we iterate over it, we will compute each value on demand, right? So the first thing we do is we need to find the first number that filter doesn't skip. So we start by asking, so filter starts by skipping over all the values until it finds one that's odd. And to do that, it has to invoke the predicate to do the transformation of the transform. And so it lazily does the work as we iterate over it. Now you might say, well, we still have state there. We've got the magnitudes and the odd magnitudes. But that's not really state. That's merely labels for part of the pipelines, right? Because they don't really contain anything. They're just a description of the data, right? And in fact, the more canonical way to write it is just inline. So the biggest odd magnitude is given by taking our range, we are transforming it to get only the absolute values, and then we're filtering the odd ones. And this is now a very functional composition. Now for the second problem, we're having two lists of integers and a number target, and we want to get two integers, one from each list, whose sum is target. So if those are our two lists and the target is 12, then the output would be 4 and 8, because 4 is in the first list, 8 in the second, and they sum to 12. And again, this is how we would write it imperatively. So we just have two nested loops. We loop over all values from the first range, all values from the second range, and check whether the sum is target. If so, we return it. Otherwise, we return that we haven't found anything. And again, to make it functional, we have to ask ourselves, what is the composition? Well, the composition is, we first need to generate all the pairs. And then we need to find the pair whose sum is target. And so let's just do that. So we use the Cartesian product view to generate all the pairs, right? This is the Cartesian product of the input ranges, which gives us a pair where like the first element ranges over all values from range 1, and the second one ranges over all elements from range 2. This is the equivalent to two nested for loops. And then we use the findIf algorithm to find the one that we care about. And note that the first line on its own, it doesn't allocate any memory. It doesn't do anything. It merely describes that the data that we care about is the Cartesian product of the two ranges. And only as we iterate over them in the findIf do we lazily get each value of the Cartesian product on demand, right? So there's no memory allocation here. The first line, like, it doesn't do eager work. Like it all happens lazily on demand. Now, unfortunately, this code is a bit clunky. So like findIf works with iterators, and we want null up, like an optional of the value, so we have to like do the weird check at the end in there. And then also the target, like we're getting pairs, so we have to like use get to extract the values and checking it, and a bit ugly. And at ThinkCell, we really want to write code like this, like in this functional program style, but this is a bit ugly. So we've got our own algorithms that are a bit more convenient to use. So we use ThinkCell's find first if, for example. We, first of all, can specify the kind of return value that we want. In this case, we want to return the value or none, which gives us directly an optional tuple, and we don't have to do any conversions, right? And similarly, we can say like find first if and then return bool, and this is like a contains. Or like return element, which gives us an iterator, or stuff like that. And then also, when we give it a predicate, it automatically unwraps tuples. And then we don't have to worry about the std_gets, right? So we can just write auto-ab and like sum them and return them in target. And like this is like really convenient, and we should look into adding that to the C++ standard library as well. But anyways, this is the standards conforming code in the standard library. Now, one benefit of writing this in the functional program style is that in C++26 we will have parallel range algorithms. And so if you want to do this entire code, because it has like our n² complexity, so you might want a parallelizer to make it faster. And it's just a one-line change, right? You just add the execution par unseq as the first argument to findIf, and now the entire code is like multi-threaded on all your CPU cores, right? And like this is really powerful. Because we just describe the data, it's very easy for the algorithms then to automatically parallelize it. We just have to switch to the parallel version of the algorithm, right? And this would be a lot harder if we had like the imperative code where we manually had the loops, right? But like by doing it declaratively, by describing what we want instead of how to get there, we can vary how we get there very easily by just adding the parallel algorithm. Now, of course, this still isn't optimal because like we are doing, it's an O(n) squared algorithm, and we can do the compute the answer linearly by using a hash map. Right? So this is where C++ isn't a pure function programming language, and what you probably want to do is a mix where you still have some state. So to do it more efficiently, we want to take a range, we want to convert that into like a lookup structure. So we create an unordered set out of it using, this is actually in std_r2, it's not a view to a range, so this should be stdr2 and not stdv2. But anyways, we create an unordered set, and then we use a findif that uses the lookup set to more efficiently get the result, right? And this is like the more canonical O(n) solution. And now we have intermediate state, but like we don't modify it. But anyways, it's no longer like purely functional. But like that's fine. It's C++. It's not a functional programming language. We should write the best code for that problem. For another example, so given a list of integers, we want to find the length of the longest contiguous subsequence of increasing numbers. So if this is our list of integers, the output will be 4, because the subsequence 2, 4, 5, 7 is the longest subsequence that keeps increasing. Now, the imperative code starts to get really hairy, right? We need to keep track of the current length and the current previous value, and also the maximum we've seen so far. And then as we iterate over it, if we can still add it to the previous one, we increment it. Otherwise, we need to start a new subsequence. Remember to reset the current length back, and also need to keep track of the previous one. And then in the end, remember that the longest contiguous subsequence might be the one at the very end. So remember this std max at the end there, because the current length might be longer than the maximum we've seen so far. This starts to get like, it's very easy to make bugs when you write this kind of code. So, functional, what is the composition? Well, we want to split the list into like multiple chunks of increasing numbers. Then we want to determine the size of each chunk and return the maximum of that. And thanks to the power of like views, this is a one-liner. We take our range and we pipe it into chunk by. Now, chunk by looks at two adjacent elements in the input. And whenever the predicate returns false, it splits them into separate sublists. So the result of chunk by is a list of lists, where the lists are split at the borders where the predicate returns false. So as long as the previous value is less than the next one, they get accumulated into one chunk. And then if it's no longer the case, we split it and split it into another thing. And again, this is entirely lazy. Right? It doesn't allocate anything. It's simply, as we iterate over the chunk by, we get subranges out of the range that are lazily computed as we do it. Now we don't want subranges, we only want the sizes. So we pipe that into transform, give it as .size, and this maps each chunk to the size of the chunk. And then we just want the maximum of all of those, and so we immediately get 4. Right? This is where like views really start to shine, when we start having like non-trivial problems that we can like very easily compose into individual views and pipe them together. Another problem of this 4 is like a classic one where you're given a string and you want to reverse all the words, so the sequences of letters, but in reverse order, but keep the words themselves in the correct order. So if the input is hello world, this would be the output. You just flip all the words, but you keep the words overall in the same order. And again, the imperative code is really hairy. We need to keep track of the boundary, check whether we're at the boundary, then eagerly compute the one, flip it in place. And it's a lot of code. And like, I didn't write that actually. I just started writing reverse words, and then Copilot just gave it to me, so I have no idea whether that's correct. But here you go. So more productive is to think about what is the composition. So the composition here is we want to split the string into words. Then we want to reverse all the chunks that are words. And then we want to put all the chunks back together. And this is how it looks like. So we start with our string, and we can split it by using chunk by. So chunk by, we're giving the left character and the right one. And if the alphaness differs between the left and the right one, it's a word boundary. So the result is the string split into the words. And note that like non-words can be multiple characters. So if you have like multiple white space or multiple punctuations, this is correctly handled, because if you're in one of those, then their alphaness is always false, right? So you only split it when the alphaness changes. And then you want to transform each chunk, namely if it's a word. So if the first character is alpha, then it is a word, and then we want to reverse the entire chunk. Otherwise, we return it unchanged. And then we're essentially done. We just need to like sort of massage it into the correct form by joining all the chunks back together. So the result of the chunk by thingy is a range of range, and join takes a range of range and returns a single range. And again, this happens lazily. So as you iterate over the range of ranges, join will just silently flatten it out. But this entire step of the pipeline didn't do anything, right? Because it's just composing of views. So we merely describe the data, right? And then the only actual execution happens when we then convert this entire thing into a std string. So the std range is 2, this has a loop, this starts iterating of it, and as we do it, we get the correct character and append them to a std string. Now, this solution is really great. It's just slight wrinkle, it doesn't compile. And it doesn't compile because in the transformation function, one time we're returning chunk reverse, and the other time we're returning chunk. And std reverse is also lazily. So in one case, we're returning a reverse view of a chunk, and in the other case, we're returning a chunk. And those are two different types, right? So it doesn't compile because we're returning two different types from the function, right? One way to fix that is to introduce eagerness. So we can eagerly create the chunks into a std string, and now we are returning a std string in both cases, but we're having intermediate heap allocations, which we don't want. There is no satisfying solution in the C++ standard library at the moment, but at ThinkCell we have our own view, so we can create conditional ranges. And this is sort of like a variant of views, right? So it's a variant of either the reverse view or the chunk, but that then also provides begin and end, which iterates over either one of the other, and is kind of smart in how it does the type erasure and the dispatch. And I plan on bringing that to the C++ standard library. We already have like a type erased range thingy, any view in the pipeline that's going to come very definitely to C++29, which you can also use, and this is just the variant case of that. But anyways, the general idea is still the same. We take our views, we lazily compose them. So this was composing algorithms, right? And the idea is we identify small building blocks for solving a problem, right? If we're doing any kind of transformation of ranges, we can use transform or filter. Like transform changes each element and filter skips element. If we want to combine ranges, we can use Cartesian product, which gives you the Cartesian product, so n times n. There's also a zip view. So zip iterates over ranges in lockstep. So if you have like multiple ranges and you want like all the first elements, all the second elements, all the third elements, this is what zip does. And then finally in C++26 we will have concat, which is just all the ranges one after the other. If you want to split ranges, there's the simple split, which just splits on an element. So you can like split a string at white space, for example, which gives you a lazy range of the subranges, or chunk by. Chunk by is really useful. You just have to know it exists and what you can do with it, but like chunk by is a really neat trick to have. Once we split the ranges, we want to join them back together, so we can use join, which just joins them back, but also join with, which also takes a separator, and this will put a separator in between each of the subranges. So like join with and split are sort of inverses, right? If you do a split on a separator and then join with on a separator, you end up where you started, just with a different type and lazily compute it. And then we can use our algorithms. So there are variants of like max and men. There are algorithms to count, check whether predicate matches, and all of those are folds. Right? Similarly, there's like accumulate, but it's not rangified yet. It will come. But there's the rangified fold left, and they all like iterate over the entire thing and like do some transformation and give you an aggregate result. And then there are searches, like you find for elements, you search for subranges, and stuff like that. And when you do that, you minimize the use of the for loop, right? Because you declaratively describe your input, and then you pass that to the algorithm that does the actual work that you want. Now let's look at composing functions. So let's say we have a function that, given a user ID, unsubscribes that from the mailing list. So we look up the user, we get its email, and then we remove that from the mailing list. And this is sort of a composition, right? We take a user ID, we get a user out of it, and then we get an email, and then we do something with an email. Right? This is very straightforward, right? And technically, this is functional programming, right? Because we compose functions to do a problem. But what if the intermediate functions can fail, right? For example, let's say we are having std optional, which either holds a t or is empty, and now the lookup of a user can fail by giving us an optional user. So not every user ID is associated with a user. Well, then the composition gets a bit more ugly because we have this if in there, right? We look up the user, and if we have one, then we get its email, and then we remove it from the subscription list. But like logically, can still be viewed as a sort of composition, right? We start with a user ID, but instead of getting a user, we get a user or nothing. And then we sort of can turn that into an email if we had a user, or nothing if we didn't have an email, right? And let's try and write this composition more directly in the code. So given a std optional user, which we get from lookup user, how do we get the optional email? Well, kind of like this. So given if you have a user, we get the email, wrap that in an optional again. Otherwise, we don't have an email, so we return std null opt. And now we've got our optional email. And this pattern, where we like want to apply a function on an optional if it has a value, is so common, optional provides a member function for that. It's called transform. So optional transform takes a function that takes the t contained in the optional and returns some other value. And it does exactly this. Like, if you have a value, we invoke the function with the value. Otherwise, we return null opt. And now we can just say, given the email, we just transform the user into an optional email by applying the member pointer user email. And the real code doesn't use the function call syntax, it uses invoke, so this all works. Now we have our optional email. And we want to conditionally invoke subscriber list.remove. Kind of like this. Right? But we can also avoid the if by using another transform. Right? We want to conditionally invoke subscriber list.remove by giving it a transform that has a side effect of removing the subscription list. Unfortunately, this one doesn't compile because the result would be an optional void, and optional void doesn't exist, so we return monostate. And monostate is sort of like void, but it's not void, so we can just return it from function and have it in an optional. And now we can also write this entire function in a sort of pipeline style. So we look up the user, which gives us a user or nothing, we transform it, which gives us an email or nothing, and then we transform it to do the action at the end. Now, what if not every user has an email address? Well, then if we transform it, we get an optional of an optional email. And sort of the first outer optional is empty if we didn't have a user to begin with, and the inner optional is empty if we did have a user, but that user didn't have an email. And then we need two ifs and like two references at the end to unwrap it all. And this is a bit silly, so we can like write a function that flattens an optional, and we can call it join, similar how like ranges join, views join, flattened nested ranges. This one flattens nested optional, because we don't really care about the different failure modes here. Like, we don't want to distinguish between users that don't exist and users that don't have an email. In either case, we don't want to do anything. So we just flatten it out by removing one layer of optionalness. And then we could do that and get our optional of our email. But that's a bit silly because it's like much smarter not to create the unnecessary nested optional to begin with. And for that, we just need to call a different member function on optional, and then. So and then is very similar to transform, except where transform takes a function that takes a t and returns some u, and then takes a function that is guaranteed to return an optional. And then it doesn't rewrap the result in optional. So if you use and then with a failable function, you don't get the double optional, right? You just get one layer of optional. So you can just write user.endThen user.email. And this will only give you an optional email. And now if we combine that into the entire pipeline, we have the lookup the user, we end then to get the email, and then we do the action. And now one really nice way of writing it this way is that we immediately see all the intermediate steps that can introduce additional failures, right? Namely, only the ones with and then. All the ones with transform, they can fail. Because if they were to fail, they would return an optional of an optional, right? And then we would notice that later on, right? Only the one with and then are the ones that introduce new failure cases. Speaking of failure, what if there's actual failure, right? Like looking up the user, the database isn't available, we get an exception. And in this case, we just want to log it, and maybe the database is available later on, so we just schedule it for some later time, right? And this is still sort of composition, but like not really, because composition requires values and not really exceptions in the functional sense. So we need to represent failure as a value and not as an exception, and we can use std expected. So std expected either holds a t, in this case it holds a value, or it holds an e, in which case it holds an error, right? So we can imagine that our lookup user function, given a user ID, either gives us a user or a db error, right, by using expected. And then we can write code like this. So like we look at the user, if we have one, we remove it, otherwise we have an error, and we handle the error. And again, we've got this composition chain, but this time, instead of nothing, we have the ORDB error, right? We have a user ID, we turn that into user ORDB error, and then we sort of turn that into an email ORDB error. And just like with optional, we want to like reify them, and just like with optional, we can do that by calling transform on the expected. So expected, transform, same deal. It takes a function, it takes the t contained in the expected and returns a u. And we just need to like use it with expected instead of optional. And in the case of an error, we just propagate the error through unchanged. So if the expected is in the error change, transform doesn't do anything. If it's not in the error case, we extract the value, pass it to the function, and store the result. And then we can write our pipeline again. So we look up the user. This gives us a user ORDB error. We transform it to get the email ORDB error, and then we get the action. And expected actually supports void in the value type, so we don't need to worry about monostate. And then in the end, if this entire pipeline failed, and if it did fail, right, like note that this is declarative. Like if this did fail, both the two transforms don't really do anything. They're merely a description of the steps we need to take to get the result, right? And this like short circuit, so to speak, right? If there's an error, we don't continue on through the pipeline. And so if you have one, we need to handle it. But like this error handling can also be moved into the pipeline. For example, there's transform error, which is just like transform, except it operates on the error channel. So if it's a value, the value is forwarded unchanged. But if it's an error, then we pass the error to the function and store a different error, right? And in this case, we can sort of use transform error as sort of like an action if there's an error, right? So in the end, we put the transform error. So if there's an error, we get the error, we do something with it, we retry it later. And it rightfully doesn't support like void in the error case, because that would mean that we silently discard errors. So we have to again explicitly return monostate. And again, this is declarative. There is no temporal relationship. Like transform error isn't called, I mean, it is called after the ones, but like the lambda isn't invoked after the other lambda, right? Like either we invoke the first two lambdas or we invoke the last one, but we don't invoke them in the order specified. Like this is a declarative pipeline, not the individual steps. And again, we can imagine code where if you query the email, this also needs the database, so this can also fail. And then we again have the thing, we've got the expected of the expected, which is kind of silly. And like again, we could flatten it out by taking our expected, and like merging the two failure cases down to one, because we don't care about which database transaction failed. Like we only want to care that it failed. But again, this is kind of silly. It's much better to call it and then, which just has the failure built in, right? So you use and then to transform it with a function that already returns an expected, and then you don't wrap it again in an expected. And again, this means in the pipeline that if we call and then for failable functions, it is really obvious which functions can fail. Only the ones with and then. The ones with transform, they cannot fail, because otherwise the pipeline would like give you different types, right? Only failable functions are ones with and then, and this makes it really obvious compared to the exceptions, like which individual steps in the pipeline can fail. And then we've got the final transform error. Now using transform error for error handling works, but it isn't ideal, because the result of a transform error is like still an expected in the error case. But it is much more natural to have an expected that is in the success case at this point, because we've handled the error, right? There is no error anymore. We just logged it, and we're going to retry it later, so everything is good at this point. Right? Now we could return an expected in the success case, but then we have an expected of an expected in the error case, right? So now we've got the nested accepted in the error case. So transform error isn't the correct case, right? So we need sort of the and then equivalent of transform error to turn the expected correctly. And this function exists. It's called or else. So or else is like and then or transform error. So it's like and then in that it doesn't like rewrap the function because the function can already fails, and it is like transform error in that it operates on the error channel. Right? So you use or else as sort of like an error handling function. This function takes the error and can do something with it, which can either fail or in this case also explicitly indicate success. And so if we use or else, we can explicitly say that, hey, this is an expected that's in the success case, right? Because we've completely handled the error. However, this monostate in the error is not really the correct type. Better would be something like no return t. So what do I mean by that? Monostate is in the C++ standard library, and it has a single value. It's a type with a single value, so it doesn't have any additional information, right? You just have this empty object. No return T is probably going to come in C++ 29. It's needed for do expressions, and it represents the absence of any values. So monostate is sort of equivalent to a tuple that is empty, no information, whereas no return T is equivalent to a variant that is empty. And such a variant cannot be constructed logically because there are no values, right? Monostate is equivalent to void in void f that does nothing, and no return T is equivalent to the void that is returned from abort, because abort doesn't really return, right? Abort doesn't give you a void, it gives you nothing, because it never gives you anything, like it gives you no return. And so when we have an expected of a T or a monostate, that is isomorphic to optional T. We either have a T or we have a monostate, but a monostate is nothing. So we either have a T or nothing. Whereas an expected of a T or no return T means the error case can never be reached. And so this is sort of isomorphic to T, right? Because we cannot construct an expected in the error case because no return has no values that we can give it to. Right? And so this is the more appropriate return type when we want to express an expected that it can never be in the error case. Now this composition works nice as long as we have the same error type. So if we do the composition, let's say we have a query value function that gives a string from the database, which can fail with DB error, and then we have a parse value function, which gives a string and gives you an int, but it can fail with a parse error. Then we cannot easily compose them, because first of all, we need to know the return type of the overall expected, right? And in this case, we can either fail with a DB error or we can fail with a parse error. So the correct error type is variant, DB error, parse error. But then we can't directly use and then to compile it, because and then requires the same error type. So we query the value, and then it doesn't work, it requires the same one. So we have to explicitly cast the query value to the return type with the variant, and then it would work. But this is really annoying, right? It would be much nicer if you had an expected that would natively support multiple errors. And then when you call and then, you will automatically accumulate the new kinds of failures of the function. And again, this goes back to that C++ isn't a pure functional programming language, so some of the stuff gets a bit clunky, but you can write your own libraries to do that, and we might see something about that in the standard library. But the general takeaways is that you can represent sort of failures using optional and expected. And then you have them reified in the type system, and you can compose them as values, right? So you can use transform to process values, transform error to process errors. You can use and then to chain them with functions that can themselves fail. So the failures is really obvious in the code now, because you just see which parts of the pipeline can introduce new failures, and or else you can use to do error handling. However, unfortunately, if you mix different kinds of failure operational optionalness, this is a bit difficult. And so if you do this composition using transform and then, you avoid all the ifs, right? Even though we intrinsically had ifs, we only wanted to do stuff in the success case, they were sort of pushed down into the function, and we just write a pipeline that declaratively specifies what to do, and the ifs are hidden inside. Finally, let's look at composing I/O. So a functional programming language like Haskell is pure. This means that all the functions are pure. So they are functions in a mathematical sense. That means when you execute them, you don't get side effects, and they will always give you the same value when you call them with the same input. That means that you cannot have global state, because at least you cannot have mutable global state, because mutation of global state would be a side effect, so it would matter whether you call a function or not. Also, you cannot have functions that interact with the outside world, because something like getchar gives you a different values every time you call it, because it depends on what the user has typed, right? So you cannot have those functions because they are not pure. This raises the obvious questions. How do you do anything, right? Because fundamentally, you need to interact with the outside world for your program to be useful. Right? How would you write this simple program which simply reads an int and writes it squared out to standard output in Haskell, or other pure functional programming language? And the answer is you can't. What you can do is you can cheat. And they sort of cheat by, instead of doing actions, you sort of represent them and manipulate lists of them. right? So instead of a readIn function that gives you an int, you get a readIn function that represents the action of reading an int. And this is a pure function because every time you call it, you get the same action of reading an int. Right? And similarly, you don't have a write-in function that writes an int. You have a write-in function that returns the action of writing an int. Right? And again, every time you call it with 42, you will get the same action that will write 42 to input. Right? Because it doesn't do anything yet. It just describes the action. Okay, but how do you then write this function? Because when you call readInt, you don't get an int, you get an action of reading an int. Right? And then you can't multiply that. Well, what you can imagine is giving this function like transform, right? So you call readInt and you transform it. So you give it a function that will get the int and return a new int, but the result is an action that will read an int and square it and gives you the squared int. And similarly, we can have and then to compose it with a function that itself returns an action, right? So you can call and then writeInt, and now the result is an action that will read an int, squared, and write it out. And all of this is pure. The only impurity happens when you actually run the actions. So at some point you call read and write square, which gives you the action, and then you call run, and this will now actually read an int, squared, and write it to standard output. And this is the only non-pure function. Like everything is pure. And so in a pure function programming language like Haskell, they just pretend the main function doesn't exist. And essentially all your Haskell main does is give you the list of actions that then the actual program is going to execute. Right? So to speak, all the execution of a Haskell program happens after the Haskell program is done executed. Because a Haskell program just gives you a list of actions, and then an actual program goes ahead and executes them. Right? But this works. Right? Like it's completely declarative. It only uses pure functions. You just have to compose actions. Now, of course, in C++, functions don't need to be pure. Right? We're not a pure functional programming language. But like, it's still a good idea to separate I/O from computation. Right? Writing a pure function that takes the input, produces some output, but it doesn't itself do any I/O. It just returns the output. And this makes it very easy to test, because you just call the function with some values, and then you assert that it returns the correct values. And it makes it much easier to swap out various input-output procedures. Right? You completely decouple the computation from the I/O. And this sort of action approach can still be useful. Right? You first declaratively compose actions, and then execute them later. You can use them I/O, but you can also use them for other things. For example, in C++ 26, we will have std execution, which gives you sort of actions about multithreading. So a sender is an action of computing some values. And we can imagine a function async readInt, which gives you a sender, which will eventually give you an int when you execute it. So it will, when you execute it, it's an action that will read an int. And you can write async writeInt, which gives you a sender that will write an int. And then you can sort of do the Haskell style thing where you compose them by calling async readInt. You can compose it with then. It's not called transform, it's called then. I have a paper about it because it should be called transform, because we call this function transform everywhere else. And then you want to like write it, so you call let value, which for some reason is the equivalent of and then. Again, it's also in my paper. So that way you compose them, and now you've got a sender that will, when executed, read an int, squared, and write it back out. And the one action is called sync wait, because you start executing the action, and then it just waits for it to complete by blocking the current thread. Now, of course, they're not meant for this kind of code, they're meant for multithreading. So, for example, we can write a function that wants to compute the 10th Fibonacci number and check whether 42 is prime, but wants to do that in parallel. So you write a function do something, which gives you a scheduler. A scheduler is like some handle to some thread pool. And when you call std execution schedule on the scheduler, you will get a sender that will complete on this thread pool. And then you want to do the computation. So A, again, this doesn't do anything, it merely describes the action. And this is an action that will compute the 10th Fibonacci number, but on some thread in a thread pool. Similarly, we can define our second action B by calling schedule, and checking whether 42 is prime. And this is another action that will execute on a thread in the thread pool and compute prime 42. And we want to wait until both of them are done, so we use when all, which takes multiple senders and waits for all of them to be done. And so far, we haven't really done anything, we've just composed action. And then the final line, we say, okay, now start executing the action and wait until they're done. Right? And this will request two threads from the thread pool and execute our two actions in parallel on it. Right? And this makes it like really nice to like parallelize work by just describing the actions and on which scheduler they're going to execute. Right? You can also go ahead and like mix them sort of with I/O, right? So we take our async read and async write and back. And now this is a function that will, again, schedule itself on some thread pool. Once it's there, we're going to execute async read int. We get this int, we compute the Fibonacci number, and then we're going to write it out, right? And this is code that will do I/O on some thread pool, right? And because it's given with schedulers, presumably async read int will not block until the user has given an int. So like it will hand the thread back to the thread pool, and then if the int actually is written, it will like resume it, and so on. And so it will like dynamically reschedule itself. And this makes it very easy to express concurrent code, but also makes it with parallel code. And it's a really nice approach to sort of like handle concurrency. So here we declaratively build plans and execute them later. And this allows us to separate I/O from computation. And that way we sort of minimize impure functions, because we just have these pure functions that manipulate actions and move the execution of them to some later code that then is actually impure. And again, this allows us to swap out the scheduler. This allows us to swap out the I/O actions and write declarative code that is still very easily testable. Now, you might think that talk seemed a bit repetitive, right? First, we looked at ranges. Ranges contain 0 or more values, and we saw views transform to change those values, as did with join to flatten nested ranges. And there is a paper in the pipeline for a transform join, which changes those values using a function that itself returns a range. So it does a transform, and then it does a join, right? We've seen optional and expected. They contain a value or nothing or an error. We can have the transform to change this value. We can have and then to change it with a value with another function that can itself return a value or nothing or an error. And we can also write a join function that flattens the nested ones. And then we saw those I/O actions, and they sort of contain a value in the future, right? They're an action that will give you a value, right? And you can use the transform to change that value, and you can use and then to change that value using another I/O action, right? And likewise, we can write a join that flattens nested I/O actions if you accidentally use transform instead of and then. And those are all very similar. And the reason those are all very similar is because those are all monads, right? Like monads are this huge, complicated thing in functional programming, but like the C++ definition is sort of really simple, right? Because a monad is just some type that has transform and then a join, right? And then we need some way to build a monad from a value, but that's like a technical detail, right? And so we can think of a monad as some sort of box of some value that can be transformed by keeping it inside the box, right? In the case of ranges, the box is that we don't have a value, we have multiple values, but we can transform all of them sort of at the same time by just giving a function that operates on a single element, which is then applied to all of them, right? So we can keep it in a range, but only operate on single values in the transformation function. In the case of optional, we might not have the value, right? But so we can't really so to get it out, we have to check whether we have it, but we can just keep it in the box by giving it a function, and then we might not invoke the function at all. Right? And in the case of the I/O action in Haskell, right, it's an action that gives you an int. It's not an int, so you can't even take the value out of the box, right? But you can still like sort of transform it inside the box by having the transform function, which somehow gets the value out of there, passes it to the function, and returns it. It's just not something you can do, right? But you don't need to, because you can just use the transformation, you can just keep it in the box. And of course, the result of all of that is still a value you can't directly access, but you can transform it again. So you sort of have a box of some value, and you can transform it, but it has to keep inside the box, right? And monads are so essential to functional programming, because monads are what enable composition. And functional programming is all about composition, so monads are essential to functional programming. But for C++, all this means is you write building blocks using efficient, optimized, and well-tested C++ code, and then you compose those building blocks using functional paradigms. Thank you.
Big round of applause. Thank you, Jonathan. Now we shall have the questions from the audience.
Yeah. And I do have the famous things cell L value, R value socks. So if you ask a question, the first 3 people that ask questions will get the socks.
So encouragement.
Yeah.
Questions? I see one there.
Can I just speak aloud?
Yeah.
It's also for the stream, yeah, for the YouTube, so please use the microphone.
Thank you for the talk. So my question is, how do you debug the like all the transfers then? Because from my experience, what I like work with ranges and so on, it's fun when it works, but when you have to actually debug it, it's well, it sucks.
Yes. Yeah. Yes. This goes back to functional programming does not map neatly to hardware. Right? You're not debugging the pipeline, you're debugging the implementation of the pipeline, which involves a bunch of nested weird iterators and SDL machinery, which isn't fun. But usually when you write it in this functional pipeline thing, you can assume that the components of the pipeline are correct. Right? It's unlikely that there's going to be a bug in the implementation of use transform. Right? It's just the bug comes from because you're giving the transformation function is wrong, right? But not the transform view itself. And then the way you debug that is you don't use the debugger, but you can, for example, use print debugging and print out your ranges after each step of the pipeline, right? And then you will immediately notice where the bug is, right? Because it's one of the steps in the pipeline. It's not you don't have to debug the for loop that goes over it and computes the maximum with all the ifs, right? You just debug the pipeline and see which of my input data is wrong, like at which step of the pipeline gets it introduced. And with C++ 23 std_print, which supports ranges natively, it's really easy. You can just write std_print some range, right, and it will print it out, provided the elements themselves are printable, right? And this is sort of how you approach it. You don't use the regular tools you would use to debug imperative code, because that's just a nightmare, right? That doesn't work. You use other tools, right? And in this case, the tool I use is just print it out, right? And then I find the bugs like that.
So we are back to debug by printing.
I mean, I'm not sure whether back to I think it's very convenient, right?
Okay, thanks.
Yeah.
Thank you.
Yeah.
We have one question here up front.
Do you have enough control over the implementation of the way these transforms and such work? Enough that it could work on embedded or something where you have to have a lot of control over the implementation to make it as efficient as possible?
Right. So the standard implementation is not as good as it could be. This isn't the fault of the implementers. And in some cases of the standard library, this is a fault of the specification. So in principle, they don't allocate and stuff like that, right? So you don't have to worry about that. It's just that to represent a lazy range, you have to use C++ iterators, which sort of create a state machine. And then you loop over, and then what you usually do is you loop over the entire state machine and completely drive it to completion. And so what the optimizer needs to do is needs to look at the code of the state machine and realize that, oh, this is just 2 for loops, right? And turn it back into the 2 for loops that you would write in the imperative code, which is a bit challenging. There are ways you can avoid that in some cases. They're just not part of the standard, but there are multiple people. I'm going to work on it. Tristan Brindle, who has another ranges library, is going to work on that. And we have 2 sort of slightly competing ideas, but they're very similar, that we're going to bring to the standard library. And the idea is simply to have the view sort of customize the for each loop itself. And then it's a matter of just inlining and you get the native code. This works in many cases where you just have a loop over the entire range or a loop with short circuits. I gave a talk about it at C++ Now, missing and future C++ range concept. That goes into detail if you're curious about that. And that way you sort of avoid the iterator overhead completely. But yes, at the moment, the standard implementation has these problems, right? Which is why I said use this for the sort of high-level building blocks, right? Not for the inner loop. And yes, it's a trade-off, unfortunately. It's not entirely free. It can be made free in more situations, but we are not there yet. Yeah.
Thanks.
Right, thank you. Any other questions? Okay, I see 2 people there.
Do you know if there are plans to add optional reference to the standard?
Yes, it is in C++ 26.
Oh, nice.
Yeah.
That was short.
Yeah.
Thank you.
Next step is going to be expected reference, presumably, and maybe optional void.
And here again.
Hi, thanks for the excellent talk. I'm just wondering if you could comment a little bit on the performance gains that the compiler can do whenever doing such functional pipelines.
Right. So there aren't performance gains in the sense of the optimizer is going to do a better job. Like usually that part is slightly worse. But what you can do is you can get massive gains by getting sort of parallelism for free. Right? Instead, just switch to the parallel version of the algorithm, and now you've got it parallelized. Right? And that will definitely offset any like minor like per thread pessimizations due to the iterator overhead. So this will give you massive performance add, and it is really easy, right? Just add like pair unsec to the thing, and now it's parallelized. In the cases where that works, it has some technical requirements. It doesn't work for all views, but in the ones where it works, that's really great. And so that's a very easy benefit you can get, and the scenarios in which it works are going to be expanded because, like, for example, NVIDIA is very much pushing that to get it like running on GPUs, right? You can use their algorithms and probably easily run them on all your GPU, and so you get like massive speed ups out of that. Right.
Okay, thank you.
Thank you. Any other questions? I have one here.
Hey, have you measured any impact on compile times when using, ranges or and monadic templates compared to like an if?
Yes. Yeah, you have an impact. I didn't need to measure it. It's compile times suffer, which is really unfortunate. It's C++ what you will do, right? Like we at ThinkCell use that heavily, and we have really nice build machines, that take care of it. So, like we're only having like a full rebuild is like 15 minutes or something. So only like that's an order of magnitude more than it should be, because C++ is just a bad language if you want fast compile times. It's just, but like I mean. They're slow anyway, so just lean into it. Like does it really matter whether it's 15 minutes or like 5 minutes? Like it's the same sort of. It's just the coffee break gets longer, Yeah.
All right, that was it. Yeah. So that was the last. Let's say this killer question was the last one. So thank you very much. Thank you, Jonathan. Again, big round of applause to Jonathan.